In this video, I will explain the integral test, a theorem that gives us a relation between series and integrals. It is motivated by this question. I begin with a function f that is continuous between 1 and infinity, and I'm going to compare a series and an improper integral, specifically the sum from n equals 1 to infinity of f of n and the improper integral from 1 to infinity of f of x with respect to x. I want to know if there is a relation between them. This is a very natural question because series and improper integrals are defined in a very similar manner. The series, or infinite sum, is defined as a limit of partial or finite sums. Specifically, I compute the sum of the same terms, but I stop at a certain cutoff k and then take the limit when k goes to infinity. And the improper integral is defined exactly the same way, as a limit of proper integrals. I calculate the integral of the same function, but I stop at a certain cutoff b, and then I take the limit when this b goes to infinity. And the similarities continue. Many of the theorems, results, and properties of series and improper integrals are very much the same. So it seems natural to ask if there is a relation between these two notions. Finding a relation would be useful, because there is a tool for integrals that we don't have for series. We can calculate the value of an improper integral if we have an expression for the antiderivative of f. So once we find this relation, we'll be able to use that tool also to say something about series. I'm going to make two assumptions to simplify things. The question can be asked for any continuous function f, but I'm going to assume the function f is positive, because in that case, I know this guarantees that both the series and the improper integral can only be either convergent or divergent to infinity. There is not a possibility of oscillation. And that simplifies things a lot, because to prove one of them is convergent, all I have to prove is that it is not infinity. So if it is bounded above, it's necessarily convergent. And second, I'm also going to assume the function is decreasing. Most of the interesting functions we use for series or integrals are actually decreasing, or at least eventually decreasing, which will be enough. And that's going to simplify the calculation in a way I will explain soon. Here is the strategy. I will first find a relation between proper integrals and finite sums, and then I will take the limit. And I'm going to do this geometrically. I've chosen here the graph of a generic function that is positive and decreasing and continuous. And in green, I have represented the area under the curve, which is the integral from 1 to 5 of this function. I want to find the relation between this integral and a finite sum. And we know that we can bound this area by bigger rectangles, which I'm going to draw in blue. Specifically, I can say that the integral is less than or equal to the area of these blue rectangles. Every rectangle has width 1. The height of the first rectangle is f of 1, the height of the second is f of 2, and then f of 3 and f of 4. So the area of all the rectangles is the sum of f of n when n goes from 1 to 4. So this picture summarizes that the integral from 1 to 5 is less than or equal to the sum of fn when n goes from 1 to 4. And notice that in order to be able to do this, I needed the function to be decreasing, so that the values of the functions at the left end point of every small interval could be the maximum of the function on that interval. I can also do the very same thing to bound the area below instead of above. Instead of using these blue rectangles, I can use these red rectangles, and then say that the green area is greater than or equal than the area of these 4 red rectangles. Again, every rectangle has width 1. The first one has height f of 2, then f of 3, f of 4, and f of 5. So the sum of the area of the red rectangles is the sum of f of n when n goes from 2 to 5. So now this picture summarizes that the integral from 1 to 5 of the function f is greater than or equal to the sum of f of n when n goes from 2 to 5. When I put both things together, I get that this partial sum, which is the area of the red rectangles, is less than or equal to this proper integral, in green, which is less than or equal to this partial sum, which is the area of the blue rectangles. So let's take those two inequalities and see what we can do with them. First, I chose 5, but I could have chosen any other integer and do the same calculation. So let's replace 5 with big N that represents an arbitrary integer. Next, I am going to take the limit as n, big N, approaches infinity. And I get this, that the series from 2 to infinity is less than or equal to the integral from 1 to infinity, which is less than or equal to the series from 1 to infinity. And I can do this because the function f is positive, and therefore these three limits, each one of them, either exist, is convergent, or is infinity. That's what allows me to pass to the limit, with the understanding that some of these things could be infinity. What I got here is that the improper integral is sandwiched between two series. Now the two series, the red and the blue series, are different, but the red series is a tail of the blue series. They only differ on the first term. So even though they have different values, what we know is that if one of them is convergent, then so is the other. And at this point, I can now use a comparison between improper integrals and infinite sums and get the result I'm looking for. If the blue series is convergent, then the improper integral in green is bounded above and therefore must be convergent as well. And if the improper integral in green is convergent, is a finite number, then the red series is bounded above and therefore must be convergent as well. I'm using the fact again that since the function is positive, this has to be convergent to a finite number or infinity. And I have concluded that one is convergent if and only if the other is convergent, and that is the theorem. The theorem, called the integral test, says the following. I've been working with functions defined starting at 1, but I could have defined them starting at any point. So let's say a is a real number, and let's say f is a function that is continuous, positive, and decreasing from a to infinity. We need continuous so that the integral is always defined, positive so that we know everything is either convergent or infinity, and decreasing so that I could write the comparison between the partial sums and the proper integrals. In that case, the theorem says that the improper integral is convergent if and only if the series is convergent. And just to say convergent, I don't need to say where the series starts. We're going to use the following notation. We're going to write a tilde between the integral and the series to indicate they're either both convergent or they're both divergent, meaning they both behave the same way. This does not mean that they are equal. If they are convergent, they're both numbers, but they are different numbers. It just means they're either both convergent, both a number, or none of them. And that's the theorem. In the next video, I will present two examples of how to use this to conclude that certain series are convergent or divergent.